You got it?
Yeah.
Okay. Definition of inductive set. First off, 1's in the set.
Why is this important?
If K is in the set, K plus 1 is in the set. Oops. That's how you know it's an inductive set. Right?
Right.
And we went over this when I first introduced an inductive set. I said, if this is all the information I give you about a set, what do you know about A?
It's inductive.
Right, well, what do you know is in A? Name some things in A.
1, 2, 3, induction.
1, 2, 3, 4, etc. You get the natural numbers. So that was our intuition that if a set is inductive, at the very least, it contains the natural numbers.
Right.
Right? The definition of the natural numbers in this class was the intersection of all inductive sets. In other words, what are the elements that we're guaranteed are in every inductive set?
1, 2, 3.
1, 2, 3, 4. Or the natural numbers. That was their definition. Right? So the natural numbers, you can think about it in a sense. It's a set of elements that have to be in every inductive set. So the natural numbers are a subset of every inductive set. So I have A is a subset of the natural numbers. Then if I can show that A is inductive, I also know that the natural numbers are a subset of A. Therefore, they're equal. Therefore, this statement is true for every natural number, which is what we're trying to prove. Okay?
Nice.
So we define A so that it's a subset of N. Then we show that A is inductive, or in other words, that N is a subset of A. Therefore, they're the same set.
Okay, that makes sense. If A is inductive, seems like this. If A is inductive, it equals N.
If A is inductive and a subset of N. Notice how we define it to be a subset of N.
How do we define it to be a subset?
A is a set of all natural numbers such that something. Everything in A is a natural number. So A is a subset of the natural numbers. Right?
This all makes sense now.
So we define A so it's a subset of natural numbers. Next thing we need to do is show that A is inductive. Or in other words, the natural numbers are a subset of A.
Okay.
Okay. So let A equal this. From here on out, we're trying to show that A is an inductive set. We already have it as a subset of natural numbers. Now let's show it's inductive. We need to show that 1's in there. And then we need to show that if K is in there, K plus 1's in there. So 2. Observe
Literally what?
that. Now, here's how you need to do this. You need to do this when you plug in 1 is equal to something is equal to this when you plug in 1. Don't break this up into 2 steps. Don't say, look, this is equal to 1 and this is equal to 1.
You just say 1 is equal to 1.
While that may work in this case, sometimes that can lead you to logical mistakes that don't really work. For example, let me give you a case where that might have been bad. If I want to show that, that's a tangent. That'll take too much space. Anyways, so I need to show that 1's in this set, right? In other words, I need to show that the sum from K equals 1 of 1 squared to 1 is equal to 1 times that times that. So observe that the sum from K equals 1 to 1 of K squared is equal to 1 squared is equal to 1 is equal to 1 times 2 times 3 over 6. 3, therefore, 1 is in A. Right? Okay. Now we need to show that if K is in A, then K plus 1's in A. How do we prove an if-then statement? We assume the condition and we show that implies a conclusion. That's how we always do it. Right? So the next thing is assume K is in A. What does it mean for K to be in A?
All N is K.
Sorry, let's not use K since K is what we get up here. So assume J is in A. Then we're going to show J plus 1's in A. So what does it mean for J to be in A?
All N equals J.
Then, if j is in A, then that literally means, the definition of being in A is that the sum from k equals 1 to whatever you are of k squared is equal to whatever you are times whatever you are plus 1 times 2 of whatever you are plus 1 over 6. That is the exact definition of what it means to be in A. This holds for whatever that number is. Does that make sense?
Yeah.
We need to show that j in A implies j plus 1 is in A. So we need to get down to, therefore, j plus 1 is in A. And our last line might be, therefore, A is inductive.
Right.
Which implies A is equal to the set of all natural numbers. So that's what we're trying to get, right? What does it mean for j plus 1 to be in A?
If you add j plus 1 at the end.
That means j plus 1 to be in A. Plug it in exactly what it means. It means that the sum from k equals 1 to j plus 1 of k squared is equal to j plus 1 times
2j plus 1. Alright.
Trying to write it out this way instead of the shorthand way so that you can see exactly what I'm trying to say.
Right.
This is exactly what it means for j plus 1 to be in A. This is what it meant for j to be in A. This is what it means for j plus 1 to be in A.
Yeah.
So I need to show that since this is true, then this is true. Almost everything up to this point has been trivial. I haven't had to think except for a little bit right here. That's the only thinking I've had to do. Other than that, I've just been asking, what's the exact definition of that? What's the exact definition of that? You should be able to get to this point in a proof by induction like that. These are easy proofs.
Which we did.
No, you didn't.
Oh yeah, no I didn't.
None of you did.
It's been a while.
Okay, that's why we're going over it. Make sure you understand this, because proof by induction, I mean, if you're going to continue your education in any significant way, you know what significant means?
Yes.
Okay. If you're going to continue your education in any significant way, you're going to be using proof by induction a lot down the road. It's a very useful tool. It's one of the most useful proof techniques there are. There's very few more useful than this. It comes up so much. Showing that the natural numbers always satisfy something is something that you do over and over and over again. It's very useful. It's not going away. And so understanding the logic of it is, I can't stress it enough. It's just, and when it comes up, it's like you hope for it because it's so easy. Because you already know everything to do except for a little piece of the puzzle. Right? Okay, so we've got to get from here to here. And this is where your own thinking has to come in. And when you have sums, it's usually pretty straightforward how you do it. This is the sum of 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to j squared. This is that same sum plus one more term.
Right.
So here's the big leap. The sum from j plus 1, or sorry, from k equals 1 to j plus 1 of k squared is equal to this exact sum.
Plus j plus 1 squared.
Does that leap make sense?
Yeah.
That's the big leap. From here on out, it's just simple plugging in an algebra. So then, we already know what this sum is. It's right there. So that's equal to j j times j plus 1 times 2j plus 1 over 6 plus j plus 1 squared. Right? Because that and that are equal. This is equal to that. So you just did that substitution right there.
I get it to look like that.
Yeah, from here on out, you're just taking this and you're playing with it to make it look like that. Which is, again, the easy part. We've done the hard part of the proof. So let's make sure you understand the hard part. Is there anything weird about what we just did? Anything that's not intuitive? Anything that's even a little bit confusing?
Well, it's not intuitive. I understand it.
Here's why it should be intuitive. How do I get from this to this?
Yeah, that part, I've always struggled with.
I mean, so ignore line 6 for a second. You're here. You know you've got to get here.
I guess my problem would be understanding summation. When I look at it, I don't take into account the definition of summation.
Well,
Yeah, so that is a problem. You need to think about what exactly that is. That's 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to j
I
squared.
didn't think of that.
And that's the same exact sum with
With
1
5
extra term. Right? Okay. So we good?
Yeah.
And then you know how to finish this out?
Yeah.
You need to see the algebra?
No.
Okay. Proof by induction. You need to see another proof by induction?
Yeah.
Yeah, I want to.
Okay.
Should I find one in the book or you?
No, I can give you one. Jeez, she is using water in it. So, just do this one.
So it's 1, J, or A.
You can use whatever letter you want.
A equals set of all J in natural numbers such that, that's such that,
Yeah.
That is true.
In set element.
summation K equals 1, K equals Wait, what did this be?
Wonderful. You're already up.
Or what did this be then?
There you go. Yeah, make sure what you're saying makes sense. Okay, first off, you don't have a sentence right there.
Okay.
And then capital L. There you go. That's a valid first line of the proof. Observe.
Is in
How? You don't get to just say one's an A.
A. Huh?
Show me one's an A.
I'm going to show you right now.
How do you know that one's an A?
I have to show you.
Well, you see that n plus
I put a
1.
comma in right here.
You can, you can write whatever you want. Just make sure you're writing valid sentences.
Just prove it before you say observe.
How do you know that one is an A? I don't agree with that statement.
Yeah.
Yeah, okay. You did exactly what I told you not to do. You're saying this is equal to this, which is the leap that we're trying to make.
Okay, watch out.
You're doing your simplifying backwards.
I know. I thought that's what you did.
If you're wanting to do that, if you want to split up like that, then you do 2 over 2 here is equal to 1 times 1 plus 1 over 2. I'm saying that this is ultimately equal to this.
Is this right?
I'm not saying this is somewhere along the lines equal to this is somewhere along the lines equal to this.
Okay.
No, this is equal to this. but no, you still, that's not what it means.
And what would you do?
Look very carefully. What does it mean for 1 to be an A?
If K equals 1.
Means that it satisfies that equation, makes it true.
Which one I just did.
So if 1 is in A, then that means 1 is a valid number to plug in for n.
Right, so 1's in the natural numbers. Observe that.
Look at the statement. What does it mean for 1 to make this statement true?
It's in the natural numbers.
I want you to look carefully at the sum.
Then it's valid at, it's true at 1. What do you mean?
Okay, what would it mean for it to be true for 10?
Then n equals 10. Oh, wait, wait.
The sum from k equals 1 to 1 of k. Because imagine if you did 10. We're not saying the sum of 10, I don't even know what you're going to put up there. N times, what do you mean n times? You didn't say what n was. Observe that, comma. So 1's an A, showing that 1's an A. You okay to say 1's an A. Or you just write 1's an A, I guess. But at least you showed your work that 1's an A before you said 1's an A.
Well, observe that 1's an A. You can see right here.
When you say observe that 1's an A, then you're saying we now know 1's an A. That's a fact that we now know. No, we don't. You're showing it.
Okay.
And then after you show it, we say, oh, 1's an A. Yeah, I agree with you now. I know it feels trivial for this one, but the point is get comfortable with it. Assume K is an A. All right. What does it mean for K to be an
Oh, yeah.
A? Oh, you can put on the next line. That's fine.
Well, I'll put it right here. Then K over. Oh, I can't do K because I'm already using K. So J. Then J over the summation of K equals 1 of J. K. Wait. Of K equals J comma J. J plus 1 in A means, wait, can't even try not to that.
Do the argument that concludes J plus 1's an A. Do it from the bottom if you need to. That's not a bad idea. You're not sure exactly how to continue.
Therefore,
A is in
is
How does that show that A is equal to N?
oh,
n's inductive, so A, if A equals n, then A is inductive.
Remember what you're trying to do. You're trying to show, I don't have a problem with you writing that as long as you understand the logic. I was checking if you understood the logic. You're trying to show that this is true for every natural number.
right,
Which means you're trying to show that A is equal to a set of all natural numbers.
right,
You defined A, so it's a subset of natural numbers.
right.
So that's what we know so far.
If it's inductive, it equals N.
How do you know that?
Because A or A is a subset of all N, and if N is a subset of all A, then they're equal.
How would an N be a subset of A?
If it's inductive.
If A is inductive, N is a subset of A?
If A is inductive, all A is in N. Because all N is all inductive sets.
All A is in N.
All A is in n, but
All A
n
is in N means A is a subset of N.
Right?
You need to show also that N is a subset of A.
Well, you show that if you prove A is inductive.
How does that show that N's in A?
If A is inductive, all N are going to be in A.
How do you know that?
Because all inductive sets are in N.
All inductive sets are in
The
N.
intersection.
R is an
All
inductive set.
intersections.
Is R in N?
All intersections.
What do you mean all intersections?
Look, if I have A and it is a subset of N, and then if I prove that all A, prove that A is inductive, then every term in A has to be in N.
I agree with you, but I want you to understand the exact definition of N and how you're getting that from inductive. The natural numbers, by definition, is the intersection of every inductive set.
Right.
Remember what set intersection
That
is?
means- Yes.
All right.
Wait, set intersection means, okay, the intersection of all these sets. Is 3.
Correct. The second thing, yeah.
Right. So, the natural numbers is a set of all inductive sets, then A is going
You
to have
are so careless with your liquid. N is the intersection of all inductive sets. Therefore, N.
every inductive set contains every member of N.
Right. So the natural numbers are a subset of any inductive set.
Okay, but they're equal.
I'm confused now.
They are 100% equal.
I don't know why I'm confused.
Only because of this. R is an inductive set. Is 1 in R.
Yeah.
If K is in R, is K plus 1 in R.
Oh, yeah, you're right. Okay, I see.
So N, the natural numbers are in every inductive set. If a set is inductive, it contains the natural numbers.
Yeah.
Because the natural numbers, by definition, are the intersection of every inductive set.
But
They are the set of elements that are in every inductive set. Therefore, if a set is inductive, N is a subset of that set.
Okay.
Does that make sense?
Yes.
That's why showing that A is inductive shows A is equal to N. You define A so it's a subset of N.
And then you.
And then
show-
if A is inductive, N is a subset of A by definition of the natural numbers.
By definition, they're equal now. Or.
Well, yeah, if I have this is a subset of this, and this is a subset of this, and the sets are equal. It's kind of like if I show X is less than or equal to Y, and Y is less than or equal to X. They're equal.
Right. Okay.
Am I losing you in that?
Oh, I don't know where I got lost.
This is the logic that you need to keep track of behind all this.
This is how it works. Okay.
All right.
So, we define A to be a subset of N. Because every member in A is in the natural numbers.
Okay.
And then, since the natural numbers is the intersection of all inductive sets, that means if there is a member of an any inductive set, like I did over here, 1, 2, 3, 1, 2, or 1, 3, or 3. The intersection of this is 3. So every inductive set, N is the, or,
N is the 3.
Sure.
right. What is this? What do you call this again?
Subset.
So N is the subset of every A. I'm sorry. N is the subset of every A. Since we define A to be the subset of N, and if we prove A is inductive, we know N is the subset of every inductive set. So
Making
since
them equal.
since every member, or since A is the subset of N, and then since A is inductive, N is now a subset of A, making them equal. And you prove that by making A an inductive set.
So you follow all that?
Yeah.
So 2 steps. Define A so it's a subset of N, and then show that A is inductive. So
I
A is a
think
subset
where
of
I
N.
get stuck is defining A. Every, when I look at it, if you're to
Some
give
of
me
those
a
are tricky
proof,
though.
if you were to give me a proof next week of inductive, I'd probably forget about defining A. And I just say, look at 1, da 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 da. And then I
Well,
go,
sometimes,
Well, keep track of your logic. What are we proving? We're proving that this is true for all natural numbers. We kind of didn't specify what we're doing in the proof one. Prove that that is true for all N in N is a better way of saying it. Right? So we say let A be the set of all natural numbers that make it true.
yeah.
So in our definition, A is already a subset of the natural numbers. And we're going to say, look, all the natural numbers that make this true is all the natural numbers. That's what you're proving from here on out, by showing that A is inductive. I don't know. If you understand all that,
Okay,
start
so
with your problem, define a set of all the natural numbers that satisfy the problem, show that 1's in there, and show that k's in there, k plus 1's in there. So it's inductive, so it is all the natural.
so my last line can be, therefore A is inductive, because that's how
Sure, as
proof
long
by
as you
induction
understand
ends.
it. Well, it ends with A is equal to N,
Right.
but
If you conclude with A is inductive, then
where to end a proof kind of depends on your audience.
okay.
End it where you feel confident that you could go back, reread it, and understand exactly what you're doing. So if you're going to specify like that, then I wrote, therefore A is inductive, showing N is a subset of A.
Showing.
What the heck is up with me with my N's and or my D's and my G's? That's so weird.
She did that check out.
I actually did that when I was proving or when I was doing homework. And the thing is every time I did and before the function.
I hate summation signs with a passion. Sorry, Gabe, I hate something today.
What?
In your talk.
Jake's a hater. He's holding a grudge against summation so he can't progress in his life.
That's what your talk was about.
My talk was about it.
His talk was too all over the place.
My talk was about don't waste time. My
Sorry.
talk was about respect yourself. My talk was about perfection is constantly progressing. My talk is about don't hate people.
James?
Did you just get up there with like 5 sets of note cards of different talks and you just went from
I actually found I ended my talk earlier than I thought, and I thought, oh, that's way to end.
There you go. Figuring out that sum. Maybe I should just have you guys write a ton of sums.
Dude, you think we learned a lot of sums in trig? I guess you taught trig. How many times did you treat sums?
I don't remember.
We
Sums and trig.
I never dealt with sums.
You don't deal with sums and trig.
I've never dealt with more sums than in this class, and we rarely deal with sums in this class.
What?
there?
I dealt with sums. Tons
Oh
of
wait,
sums.
we dealt with sums in
Discrete
calculus, I guess, all the time.
Keep going.
Wait, where are we?
Oh my gosh.
Okay, throw something at you.
So,
Make your statement true.
it's true.
No, it's not. Do the algebra on what you just wrote. Expand that out.
J squared plus J plus 2 over 6. Is that what you want?
Oh, wow. That's pretty crazy, though. That's how you do that. So you're telling me if I have 6 plus 1 times 3 plus 4.
You're saying this?
Oh, there we go. Now I understand what you're saying.
Okay. Pressure. Wait, you say then k plus 1 and a means?
Then what?
Then k plus 1. I'm trying to show. What do I say on this sentence?
Here's the
Well,
first
J
time
plus
that you
one.
have to think. You need to show that since this is true, this is true.
I know.
So how do I go from this to this?
Oh, do I just say, oh yeah, then j plus 1. That's good. 8k equals j times j plus 1 over 2 plus j plus 1. Literally set j. Get on the denominators.
No. Look at that line and fix it and make it make sense.
K equals 1.
You can do that if you want. Where are you starting your sum from?
algebra on this line, or do I have to have that?
Well, you have to give me a statement, whatever you do.
I'm kind of confused on adding j plus 1.
G plus one is.
How does that
So he
fit?
was right here.
Plus one more term.
He had j, the sum from k equals 1 to j is equal to this, right? He's trying to show that this equals this.
Yeah.
Look, one way of thinking about it is I tell you x equals 13. Now we need to figure out what x plus 1 equals.
Oh, I figured it out.
Okay, I understand that, but I don't see how j plus 1 is the next term. I see because this is a term, right?
Okay.
So j plus 1.
The sum from 1 to j is equal to this. You're trying to figure out what the sum from 1 to j plus 1
Your
equals.
7 is wrong.
Look, in other words, here, let's write this out very explicitly. Let me see your research. He says 1 plus 2 plus 3 plus dot 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 plus j minus 1 plus j is equal to j times j plus 1 over 2. Now I'm telling him to figure out what is 1 plus 2 plus 3 plus dot 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 plus j minus 1 plus j plus j plus 1 is equal to, right?
Okay.
So we do that.
I'm telling him to show that this is equal to, do this capital T, screw me up, is equal to j plus 1 times j plus 2 over 2.
Yeah.
This is what you know. You're trying to prove this.
Very nice.
How do I go from this to this?
Oh, yeah.
I need to add j plus 1 to both sides,
You
right?
didn't finish.
So then, 1 plus dot 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 plus j plus 1 is equal to this
You don't have any more
plus j plus
to.
1.
Sorry.
I have way more room to improve. It's called the next lesson.
And now I just need to show that this and this are actually the same thing.
Me, I have lots of room to improve.
Okay.
That's the leap he's making. How do I go from the sum? Here I have, this is this line, right here, same thing.
Yep.
I'm trying to get to the bottom line, which is this line. How do I do that? I add j plus 1 to both sides. That's what this is.
Okay.
So add j plus 1 to both sides, see if this actually ends up giving you that. Oh, yep, it does. We're done.
I don't know how to explain it, but what's weird, like I understand that, but what's weird to me is this, this is a term. That right there is this. And so when I look at this, I think
You're what?
J,
No.
I think J
Okay.
plus
I built the
1.
last.
That's how I see it, is I'm seeing this in for J.
I built the whole base, so it'll be really right. It's literally.
Because it's a term.
It's
Because J, because
Oh,
you
you're
have
right.
J, which is this,
J.
plus 1.
I want
Let's
to
clean up terminology. This is not a term in your sum. This is the result of the sum. If you add up all 1 elements, you get this. If you add up all j elements, you get this.
Okay.
That tree's
The
gone.
question is, if you add up all j plus 1 elements, do you get this?
I'm gonna.
Does that make sense? I mean, it's so equivalent to, I say, I tell you that x is equal to 13.
To count after school.
Prove x plus 1 is equal to 14. Show that if this is true, then this is true. What do?
Yeah.
You add on both sides. You say, okay, x plus 1, what is that equal to? That's equal to 13 plus 1. Oh, that does equal 14. Yep, it works.
From down there.
So you're showing that the sum of this is equal to that plus that, which is equal to this. Oh, it does work.
This is what
Same exact
this is what
feature.
Ames I did to me was break down boxes
Just add one to both sides of the equation.
because you gotta create the structure before you put paper on.
In this case, you're not adding to both sides of the equation, you're adding j plus 1.
Just duct tape the crap out.
The
of
previous
all the
one we
boxes
added j plus 1
tree.
squared to both sides of
Form
the
the
equation.
boxes, the format of the tree.
But same thing.
You get Elmer's glue and water.
That makes
mix it up
sense.
in a solution. And
All
literally
right.
take that brown paper and paint it. And then push
So do another proof by induction?
and just paste it on.
Alright,
Just wrap it like 3 layers.
Yeah. From there on out, just out.
And then from there, you gotta figure out. See crap like this? I wish we could just take this plant and just stick it on top. Or as
Why don't you just get?
Or that side right
Second
there.
branch.
Why don't you just?
All
get
right.
every-
Enough with talking about trees.
Why don't you just get?
Do we need to do another proof by
Let's
induction?
do one that isn't so easy to set A to be our term. Because I remember last time when we were doing proof by
Second
induction,
should be our term.
A does not always look like this. A can look like,
Look, Jake.
set A to be M in and such that.
Well, okay, so let's do another one. Let's prove that the sum of two natural numbers is a natural number.
Okay.
Oh, didn't we already do that?
Yeah, we've already done all these.
Sum of two natural
You
numbers
erase
is
it
a
more.
natural number.
And you can be slapped.
Wait, what? Didn't we do that at the very beginning?
Yeah, we did all of these at the very beginning. I haven't put something new up here.
First day.
Still do.
First day, we talked about proof by induction. Very first day. Yeah, we're going back to day 1 here. That's the regression. What do you want back? That we talked about proof by induction first day. There's no way we didn't. There's no way this isn't preliminary stuff. Okay, prove that the sum of natural numbers is a natural number.
Prove that. And let's just do it.
Why didn't you just do A plus B equals C where A, B, and C are natural numbers?
That's kind of a weird way to do it.
Tell me that's
weird.
weird.
Okay, first off, that's just not true. I can find 3 natural numbers where that's not true. 1 plus 1 is not equal to 1. So, no, that's a load of crap.
What? Let A be set.
Now, here's where we're going to have trouble defining your A.
I will dominate this.
Alright.
Of all n and n in natural numbers
Where that is true.
such that n plus n is. Okay, wait, before you go.
Yeah, you're wrong.
Okay, then what
Let me help you.
is-
I'm not telling you the answer. I'm showing you how you're wrong. What if m is always 1 and then n is all the natural numbers? Then this is a set of all natural numbers. But that doesn't satisfy this statement.
Okay.
Did you understand what I said?
Mm-hmm.
Alright.
So,
For any M.
for any n in the natural numbers, such that. No,
You are killing me.
what do you do again? This.
Sure. Both of them are perfectly valid.
Such that n plus n
What's n?
n is a natural number.
I don't see that right now there anywhere.
I know that you're only supposed to include n here, and we're saying
Why?
n plus a number is a natural number.
Why are you only supposed to include n?
Because I remember that's how you did it.
You ready for a hint?
Yeah.
Alright.
So do we even decide a set? Design a set?
What about n?
Yeah, prove by induction. You're always proving that the set is equal to the natural number.
Let n percent.
Let the inductive set be n in n such that.
No, other way for set building notation. Vertical line or colon.
Such that.
Oh, I see.
Ah! There we go.
Assume in it. No, show. That one is in. What? How do you do that?
Good question. How do you do that?
You use an identity. Don't you use
No, you just think about what exactly.
what does it mean for and no.
Yeah, what does it mean for 1 to be an A?
Either of these have to be
N or
0.
What?
One's not in this.
No, it means that n or n.
It means that 1 or n plus 1 is in n.
If 1 is in A,
Oh, shut up, Cat.
So you gotta go if. You
what do you mean
see?
if? You need to prove that n plus 1 is in A. Exactly what you said.
Oh, you go n plus 1 is in, or you say
Oh, yeah.
observe
Observe.
that.
Means.
N plus 1 means n equals 1.
That's-
Observe 7 plus 1 means n equals 1.
Yeah.
Observe n plus
Observe
1
n
is.
plus
That is the most random statement I've ever read.
I'm trying to show that it's m plus a number. we
No,
call
just
it
say n plus
natural
1
number.
is in n.
Assume n plus 1 is an n.
Yes. Use your definition,
Now you
right?
gotta prove it.
Use your
Not
definition.
prove. Oh, yeah. Oh, use your definition. Observe, not even assume.
But how do you know n
Because
plus 1
of the
is in n?
definition.
How do you know that n plus 1 is in n?
The definition
Because
doesn't
1
say
is a natural number, we know that 1 is in the natural numbers.
Yeah, but how do you know that n plus 1 is a natural number?
Because of that.
Remember what you're trying to prove.
You're
You're trying to prove that when you add two natural numbers together, you get a natural number.
We're trying to prove that this inductive set is inductive.
Hold on, big picture proof. We're trying to prove that the sum of two natural numbers is a natural.
Yeah.
That's what we're trying to prove.
Yeah.
So we're trying to show that a natural number plus any natural number is a natural number. So we grab some arbitrary natural number. We say let A be the set of all natural numbers I can add to that thing and still get a natural number. How do I know that I can add 1 to that thing and still get a natural number?
Because n is a natural number. 1 is a natural number.
That's
How
what
does,
I'm trying to
what does that
prove.
mean about n plus 1 being a natural number?
Oh, right.
Just because 1's a natural number doesn't mean 10,000 plus 1's a natural number.
I thought there's an identity that says
This is
This
all
is-
natural
this is
numbers,
what we're
you can
proving.
add 1 and get a natural number.
Yeah, this is it. This
How do you
is
know
how
that you
we
can do
prove
that?
that
I
identity.
thought we proved that.
No, this is how we're proving that identity.
Did you use?
Oh.
So this
What is the definition of n?
Inductive. Or of
It's
n.
a set of all natural numbers.
Is the-
That's what we're defining it to be.
It's
N is the set of all natural numbers, but what's its definition?
intersection of all inductive sets.
So it's the set of all elements in every inductive
And
set.
every inductive set.
So n
contains
is
one.
inductive, right? What does it mean for n to be inductive?
It contains 1.
It contains 1, and
It contains k plus 1.
if it contains k, then it contains k plus 1.
Right.
Does it contain m?
Yes.
Yes.
So then it contains m plus 1.
Wait. Then how do you write that?
Because
Observe that n plus 1 is in n,
Because n is inductive.
since m is in n, And n is inductive,
Oh my goodness. Okay.
right?
Right. Then n equals 1.
Assume K is in.
No, so 1 is in A.
We just proved that right here. Right here we're going to say that.
Right. Sure. Most people would put then or therefore, not observe. It's a conclusion of the previous line. Shut up, one tonight.
Assume. Then k plus 1 and a
N
means.
plus K.
Huh? What do it be? N plus k plus 1.
If K is in N, then is
Oh,
N plus K?
That means.
Just put on your next one. Right?
Sure. I mean, you can split sentences however you want.
No, I mean M is N plus K is. I don't know where to go this in my mind it makes sense.
Then m, yeah, exactly that. N plus k is a natural number. That's exactly what it means for k to be an A. A is a set of all natural numbers that you can add to m and still get a natural number.
Now I just shot k plus 1, isn't it?
I don't know. What does it mean for k plus 1 to be an
It means that M plus K plus 1.
Well, look, if you go n plus k plus 1, you can make that equal n plus 1 plus k. And we know n plus 1 plus k. And no k is it?
So now we know that 1 plus k.
A? You are basically there. You're killing me. Help me
Just
out right.
right out the end of the proof.
What's the next line?
Then n plus k plus 1 is
How do you know that?
That's why I don't know.
What's the definition of n?
It means it's the.
M is in the
Oh!
Oh!
The definition of n is 1 is in.
I mean, if you want to clean it up so it's obvious what you're doing, put parentheses there. Then a natural number plus 1. If a natural number,
Oh my.
if that number's in n, then that number plus 1's in n. That's what it means for it to be an
How
inductive
do you
set.
know that a natural number plus 1 is inductive or is in n?
Because n is inductive. It's the intersection of all inductive sets.
Oh yeah, because
By our definition of the natural numbers, if k is in the natural numbers,
you
k
literally
plus
like
1
you
is
use
in
it
the
to prove itself. Oh, it's because you're doing with n.
natural. You're always using the fact that n is inductive. Therefore, A is inductive. Short. There you go. Not too bad. So you have the same basic thinking over and over again?
Yeah,
Yes.
And this was a nice one where you didn't even have to think except for coming up with these two lines. There was no middle work.
There was still trying to think that an
No, we
inductive
just use
set.
the definition exactly.
Well, yeah, I'm trying to think, but in your writing, you literally didn't have anything in there. You said, assume k plus n is in A. And you were trying to get to, then k plus m plus 1 is in A. You're trying to get from here to here, which there was no work to do that. Except in your writing. But anyways, there we go. So the sum of two natural numbers is a natural number. It's not proof. So there's a one that's not using sums. So are we good with these proof by inductions? Are we ready to move forward with our lives?
Yeah.
Are there any other questions on your test that you felt like were pulled up? Did anyone redo the problem that I was going to give you credit for if you redid? All the test problems?
Were pulled up.
Oh, geez.
Nah, James, not 1.3, number 5.
I think this one was the best one I had so far.
You don't understand what you did wrong here?
Oh, I understand what I did wrong.
It's beautiful.
Okay.
Shadow acting about doing Shadow.
What?
I haven't looked over it yet.
Since
went
I-
doing the test, all the problems were
I want to keep my sleep schedule over the break, but I don't know what to do.
Well, read
these.
So,
through it all.
Read your
And
first
then-
minutes.
If you get stuck,
Why?
I thought you guys looked over it to see what made sense.
Huh?
What didn't make sense.
that night. But I pretty much minutes. I'll just fall asleep if I read 15 minutes in the morning.
Before you go shower,
I shower, then I
sit on the
still
hard
fall asleep.
chair,
Okay.
and then read 15 minutes.
But I was thinking about going through all my calculus homework.
Fall asleep reading.
Why would you want to wake up at 6 o'clock in the morning?
I told you I already have a habit. Like I woke up at 6 o'clock this morning and didn't even need to.
Go jump on and play games.
Okay. All right, if we're good with chapter 2 stuff, let's move on to chapter 3. So any other questions related to chapter 2?
And that was convergence.
I actually.
Chapter 2, I'm not sure if that's what they call it. I think they just call it limits.
Convergence, limit, same thing. Dude, all this crap all pertains. Look how many ends I have in this proof by
Donnie.
proof of convergence.
Yeah.
I
You should draw in the morning.
Understanding.
Convergence sequences, that was
Yeah.
chapter 2.
I can do that too. Did I tell you that I wanted to start drawing again?
Yeah, and you should invite me when you do, so I can.
What should I draw? I had an idea to draw Utah Utes football players.
I have really hard. Drawing people's hearts.
I know.
Why
I'm a
don't
pretty
you-
good artist.
You are?
Why don't you draw
You
a
should have seen my
Utah
pictures
Utes
last
helmet?
year. I was thinking about
I'm
that.
having a hard time
Your
understanding.
pictures last year?
What does this mean?
You
How
did
do I
draw.
show it?
You did. You just did the notes.
Yeah.
I'm assuming that F is from the real numbers to the real numbers.
You should
So
draw.
remember, we're not in
football helmet.
baby school
Football
anymore.
helmet.
So you need to say the
And you
function.
should do
Your
it
function
with
is from the real numbers
Almost
to the real
charcoal
numbers
pencils.
by
So
this,
that you
right?
have a completely
Yeah,
black
so I'm
helmet.
wondering, how do I?
So remember what
of that? Like, I don't even know what
Should make the
think
background
what this
black.
is.
So first off, remember fundamentally what a function is. It's a set of ordered pairs,
Set of
Black
words.
helmet.
right? And every left-hand element is
Background.
from here, and this tells you how to get the right-hand element.
So it's dark.
So you take
So-
left hand element, plug them into here,
That's
Take
what
a
you
left-hand
should
element.
draw.
2.
2.
By
Alright,
the
what
way,
does
you're
2
gonna
go
go
to?
over to my house. and
Well,
walk
2
in.
goes to check our conditions.
As far as I know, every
Which
night.
condition is this 2 satisfy? This
Well,
one.
James is like,
So it gives us.
You need to invite people, your classmates over to
Okay.
play ball again.
So if you were graphing,
And I'm just like-
however you want to do that, then you know.
That,
Dude,
Two
wants
goes
to
to
do
four.
it again.
That's a point on your graph.
that was me. I was like,
Right.
okay.
Okay.
And he's just like, people need to know the real you.
All right. What about 0?
They couldn't handle
Still 2.
What?
Should we seriously like do a class game?
Or, sorry, 0.
drama
0.
class game night.
Okay, so we know 0, 0. So
Or-
what about 1?
20.
Okay.
What?
1 is
No.
1.
1. So you know 1, 1.
Because they killed the experienced mafia players.
Okay.
So
Dude, we
for
could
any
play,
number you
uh,
pick greater than or equal to
Birdbox.
0, you're using this one, right?
That's
Okay.
fun.
So you're using this one for every
If you're
number
gonna
from
play
here
room
on.
box, then might as
So-
well play 2 rooms and a booth.
What if, so, okay, so
Yeah,
You're using x
Returns and moves is fun.
from 0 onward. For all x's greater than or equal
How
to
was you
0,
gonna tell
for
you?
all
That's
these
easy
x's,
practice.
I know.
So,
you're
okay.
using
I wonder
x
if
squared,
I could.
which
be
is
like,
a
hey,
problem, right?
Let's practice Thursday.
you only have
but
half
let's
the graph.
practice Friday instead of Thursday.
Then if
But
x
we'll
is
probably
less
say
than
half
0, so
work.
1
We'll
half.
probably do 3.
1/2 not less than 0.
Oh,
Negative 1 is
negative
less than 0.
You're right.
So
we
when we
can't
plug in
just-
negative 1,
I
what
need
do
to
we get?
build the whole stage
0.
this week.
So negative 1,
What
0.
if we go to sushi and we're
When we plug in -2, what do we get?
30.
Oh, we get negative.
I committed
-1.
moving my sister Sarah out of her house from 4
Oh,
to
It's
6.
not a parabola. This is a line. This is a parabola. This is a line.
And I said 6 because I was
This line looks like an open hole here. Doesn't include that one, and then looks like this.
which probably would have.
And then it says,
We would have.
pick the
Probably
values
left, right,
that are
that maybe.
continuous.
And by the way,
It's
instead of
continuous
being
everywhere
what
except for
should
right
have done,
here.
or should
Everywhere except for
maybe
0.
after practice,
So what if,
go to start.
what if this was like a number? Or what if this was?
It's opening night.
Say this was just 5.
I know, I can't.
Okay, so then we get 5 when we plug in any number greater than or equal to 0.
So it'd just be a line.
Right,
Here we go, 5, here it is, starting right here. going up.
Grandpa.
So it's
his
continuous
family.
everywhere.
25.
Yeah, I guess the
Yes,
missionary
zero.
somehow got invited.
On Sunday.
Right?
Okay, now I can look at the phones.
On Monday.
That's 24. Just kidding, that's the 22nd.
Are you aware that?
That's the 22nd.
No, it's not. It's the 23rd.
Christmas is on the 25th.
Okay, so on this
Yeah,
problem right
Wednesday.
here, it says, at what
It's on the
point is this
23rd.
function?
Yeah, yeah.
Whoa.
in that
You do
function?
stuff.
Okay, so let's write out that function exactly.
Should figure out what the next is.
Maybe
So
we
notice
should
that function's
go to
domain is
secret
not all real
bring it home
numbers.
for practice.
Right?
Not all real.
That's my.
Oh my goodness,
You're very
I didn't
good.
even see that.
Huh?
That is a function, what's it from?
Cheeseburger.
0.
Better than
I
62.
agree 100%. So let's go to in and out and secret.
I didn't even see that.
Grab some food.
Oh.
By f of
I made
x.
Christmas
So I can
crackers
only
today.
pick out either right?
Yeah.
I made Christmas crackers.
It only makes sense to use its domain.
Yeah.
Domain is a set of all left-hand values.
Okay.
No.
And then it is 11 if 0
My point
is
is
less than or
approximately
equal to
11,
x,
I'm so hungry.
when x is
Oh.
less than or equal to 1.
I got there for
And then it
Christmas.
is x if
Do you guys pick names?
I'm getting
1 is less than x.
Roku.
Okay. So now,
Just,
look at what this looks
get
like
some
if you need to
TV
graph how we can
Download this.
Now notice we only care about from 0 to 2. So here's 0, here's 1, here's 2. This is the only place where our function's defined. You didn't know if it doesn't make any sense, bring it over here.
Not for a long time.
Oh
Correct.
Right? This is the whole
I
domain.
have over 2 years.
Okay.
It has
So,
a big
if x is between 0 and 1, including them, we do 11.
There's my grandparents.
So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Not anymore.
Alright. So from 0 to 1, it's 11.
Yeah.
So it's
in
solid
the
dot,
neighborhoods.
solid dot.
You know where you walk in.
And then
the
x
Papa's room
from 1 to 2. Well, what does x look like?
Any number.
into our nice
Well,
house.
when we graph x,
And
no.
then there's the
It's
little
just the
sliding
solid
stairs that
block.
go to the old
This,
house.
I messed up my scaling, but going back to
So
graphing
here's
y
Papa's
equals
room right
x.
here. So you walk in,
How do you graph the function
mine,
f of
there's
x is
this,
equal
and
to
then the
x?
stairs that go up there.
When you
So
plug in 1, you
here's
get 1.
Papa's
When you
room,
plug in
mine
2,
right
you
there.
get 2. When you plug in 3, you get 3. It's just a line like that.
Yeah.
So you could see
Yeah.
how.
So it's just a line like that,
Yeah.
starting from here.
And ending
I
in 2.
would
And ending at
just
2.
speak out. I'm too lazy.
It's like that. Now my scale's really
There's
messed
no
up
use for it.
here, so don't
Yeah,
let it
I see.
confuse you how I draw it, because it's going to be like this,
Yeah.
because my scale's weird.
Yeah. So it is continuous everywhere but 0, 1, and 2. Justify my answer. Well, how do I justify my
Are
answer?
you gonna come watch Lord of the Rings at my house? In the theater seats?
I will.
can't-
It's continuous everywhere except for 1.
The
It's not
second
continuous
half
at
of
0.
number 2.
Or it is continuous at 0. It's
Why?
continuous at 2.
Why?
Every
Well,
sequence, because what's the
You got-
definition of continuous?
The first one and half. the second.
There is a sequence.
Oh, you did?
Every sequence that goes to the point
2 months ago.
in the domain,
And
then the
we
image of the
Then
sequence
you
goes
can
to
watch
the
it
point.
again.
So pick it. So we're talking
How
about
long
2,
is
right?
2 and 3.
Okay.
Pick a sequence in the domain that converges to 2. So
I don't like when it's
it
very
gets
long.
closer and closer to 2.
But they're not.
Okay.
Then the
They're
image of
extended
that thing is
versions.
going to get closer and closer to whatever
They're
comes out.
extended versions.
I know.
How do we know it gets closer? Because of this?
I don't really like
Well-
this, but I really like the end
I
of
mean,
the first
you
one.
know because it's
Well,
polynomial.
it just builds.
I mean, look,
and
here's
we
how we
already
can prove it. It's
built
continuous at
every
2.
single-
Let's check 2
Yeah.
specifically, right?
Yep.
1.
It's, I don't know.
Let's
It's see.
x n
Didn't you watch
From-
Lord of the Rings?
in our domain,
Uh,
0, 2.
Extended versions.
Sorry, this is sequence. let xn in our domain such that the limit of xn
I think I watched the reviews for the first time.
is equal to 2. We're proving it's continuous at 2.
I remember.
So here's a sequence in the domain that converges to 2.
And then Jason got, last year Jason got me the
Then-
movies and Harry Potter.
The limit
For Christmas.
of
Yeah,
f of
that's glorious
xn
together. Dude, I have good Christmases. Just
Yeah,
good
you guys go.
is equal to. Notice
You
eventually
guys go ham.
any sequence we have in the domain that converges to 2,
Like your presents.
it eventually gets past 1. And so we can look at a subsequence from this point on.
Just what they
So
are.
the
Don't you
limit
guys
of
call
f
that
of
limit or
xn
something?
equals the limit of some subsequence f of x
forget
and
what it
k,
is
so
this
we can
year.
ignore the
I spelled
values
it
that were
20 bucks.
there.
But I think it was like.
Kind of doing a really rough
And is
argument
that
here.
way over? Oh, your limit
Is
was
equal
60.
to.
Our limit
What is f of x and k?
150
So
for
if
kids and
all of
175
our
for
x
adults,
and
but
k's
and for-
are after 1, what does the function give us?
After one.
but-
Yeah,
Gives
I
us,
spent 120 on that.
gives us x and k, whatever we plugged in.
120.
yeah.
See, you.
So it just gives us
you
back
sub
x and
divide
k.
stuff.
Huh?
Yeah, you sub.
Okay.
So
Like,
it equals
we
the
got a
limit
couple
of
people-
that. But what is the limit of
reality
that?
sets. Those are like 300 questions.
Yeah.
And then
Equal
we
to
got
2.
close and whatever else was on the wish list. Like,
Which is equal to f of 2.
we got somebody
And
an
after two
iPad.
is.
Wait, do you guys draw names?
Just 2.
Yeah, I rap for
Right.
everyone, so I know.
So
who
the
everyone
limit
has
of the sequence,
and what they get. Anyway, we literally bought.
if the limit of the sequence
and
is the number,
iPads
then
and
the image
more
of the
clothes
limit is the
and
image of the number.
stuff for one person.
That's what needs to be
These totals
continuous.
are like
So we just proved it's
$200
continuous at 2.
Does your pop about
At what point is this function
yeah.
continuous at?
Well,
It's at 2, and then I use this
James
exact
does
same
whatever he
for.
does with
It's
it.
continuous everywhere except for 1.
Does Uncle
Probably
James draw
from
with
little
you
kids,
guys?
of course, but like Diane, Nathan, they pay for the stuff.
Then why is it asking
Huh?
for what point?
Does
At what point
Uncle
is this
James
function
join in your
continuous?
It's continuous
Yeah,
at
Joe's name is- In fact.
It's continuous at the point
Just tip.
0, 1,
Union.
union
Crap.
1, 2. Those are the points it's
Yeah,
continuous at.
different.
Every point except for 1 in the domain.
I see.
I've done 3.
Does that make sense?
Yeah. It's just their wording. They make you think
Well,
that they're
I've
looking
done
at
3
top
and some parts. And, well, last night I did two.
Which is-
But this was one,
what through me.
that was one person.
Well,
And like,
stop trying to guess the answer based off of how they ask the questions. Just answer the
Please
question.
was
keep
one.
me track of my presents.
this was one.
Okay.
That I did.
Good with that?
In fact, that was probably.
Ready to move on?
And then I did that for a boy, with a carrot.
Yeah, I did.
Because it's good enough.
Alright. Let's move on. Start covering chapter 3 material again. Let's remember where we were last time. So last time we were going over the,
Definition of continuous.
not the definition of continuous, we covered that. We ended doing the, not intermediate value theorem, the extreme value theorem. So we were trying to prove the extreme value theorem. And the extreme value theorem basically says, so prove if f is a function from a closed interval to the real numbers. So if f from a, b to r is continuous, then f achieves the maximum end. We'll just say, we'll just do the max case,
Yeah.
and then the min follows. F has a max.
And if it has a max and a min, then it's bounded.
No, not necessarily. Well, yeah, that is true. But
Okay.
that has nothing to do with what we're saying.
Uh,
If f is a function on a closed interval, and it's continuous, then it achieves a maximum and a minimum on that closed interval.
Can't you just say because it's closed, then it has a maximum?
Be careful what we're saying. So let me give you a picture of what we're saying. Pick some closed interval. Here's A, here's B. We have some function on that interval. Here it is, well, except for only cut it off from there to there. So we're saying if we got a continuous function on this interval, then the function achieves a minimum right there and a maximum right there. It achieves a max and a min. Now this isn't trivial. For example, think about the function.
I'm confused what you're saying though, because that doesn't necessarily make sense. If it's just x equals 2 through the interval a to b, that doesn't have a max. The only member that's 2.
Say that again.
If our graph is x equals 2,
If our graph is, so we're saying
or y equals 2.
f of x equals 2.
Yeah.
At what interval?
Through 1 to 2.
From 1 to 2.
Yeah.
So what is that function? Ooh, that was terrible. From 1 to 2, our function looks like this.
That doesn't have max.
What's the max?
2.
2. What's the min?
2.
2. Sure it does. Now let's look at a case where it doesn't have a max, so that we see that this isn't trivial. Let's look at the function f of x equals 1 over x. And we'll look at it f on the interval from 0 to 1 to r.
Wouldn't 0 be its max? Or, sorry.
1 wouldn't.
One.
What does this look like? We'll make this 1. So we're starting there. When you plug in 1, you get 1, right? When you plug in 1, you get 1. Okay. What happens when you plug in 1/2? You get 2. What happens when you plug in 1/3? You get 3. What happens when you plug in 1/4? You get 4. What happens when you plug in 1/100? You get 100. So it looks like this. It tends towards
That doesn't
it.
have a max.
Yeah, 1 divided by 1 over 100 is 100.
But it has a min.
It has a min, but it doesn't have a max.
Oh,
So what the heck? Doesn't that already disprove our theorem?
I guess it has a max somewhere.
No, it doesn't have a max. It's not bounded, so it can't have a max.
so
This isn't a continuous function on this interval.
Yeah, but-
This function is not continuous at 0. So if f from a to b, that's an a, sorry, not 0.
Oh, is it?
If f from a to b is continuous, then f always has a max and a min.
Right.
So here's an example where it didn't. Well, we cheated. This isn't continuous at 0.
Right. If a was 0. Oh, and it is.
Okay, 0 to 1.
Could it, well, okay, what if we didn't, okay. What if we didn't include 0?
If it was 0.00001, then it has a max member.
Well, if you made this like -1, we still have the same problem. It's not continuous at 0.
Yeah.
But if you're saying, what if we made this 1/2? Well, yeah, now it's a continuous function, so it's going to work. It's going to achieve a max and a min.
Saying what if you just don't include 0?
That doesn't include 0.
I'm saying, okay, so if you have your parentheses that are curved, then it doesn't include 0.
Oh, you're saying do everything but 0?
Yes.
Sure.
Then it's continuous, right? And then it has a max.
That's not a closed interval, though.
Oh.
So if f is a function on a closed interval that's also continuous, then we're guaranteed it always achieves a max and a min. That's what we're proving.
Let's do it.
So, you understand the question and you see how it's not trivial?
Yeah.
I feel like it's trivial. Like it's obvious.
Why is that obvious?
Well,
Well,
it is kind of obvious. Well, it's kind of, it
is
makes
it
sense.
not?
We see how it couldn't work. We see where it couldn't work.
Well, I gave you a case that was kind of weird.
Well, it's not continuous, so I don't care.
How do you know it's not continuous? Prove to me it's not continuous.
0 to 1?
So,
Of
let's go back to
x.
the one I said. If I have f from 0 to 1 to r by f of x equals 1 over x, that's not continuous at 0?
No.
Prove it.
You could.
Could you?
Yeah?
You could, but I don't feel like that's a trivial proof.
Well, I don't care about
And
that.
that was just one. you
Because
shouldn't
it's
care about that.
continuous. Or it's not continuous.
How do you know it's not continuous at 0?
Because we proved it last.
We're gonna have to prove that it is continuous.
It's not
You
continuous at
assume-
0.
You assume by.
No, what I'm saying is we gotta prove that our interval is continuous. To get the maximum.
This interval is continuous?
No.
No, come on, our proof.
An interval is, there's no such thing as a continuous interval. A function is continuous.
It's.
Doesn't make sense.
Function
It's
continuous
continuous.
over the interval is what I'm saying.
It's
Okay.
given that it's continuous.
Yeah, so we have f is a continuous function on a closed interval. We need to prove that then the function's values achieve a maximum and a minimum.
Yeah, let's prove it.
So the way that we were splitting this up is we were first going to show that it's bounded, and then we're going to show that it achieves a max.
Well,
We're splitting it up into
if
two
it is
pieces.
bounded, it has a max. Right?
If it is
Prove that.
bounded, it has a supremum. But then does the set contain its supremum is the next question. So we're breaking this up into two things. So remember that we use this shorthand for the image. F from A to B. This is all the things that we get out, right? You good with that notation? So first off, we're showing that this thing's bounded. So we're going to show that this thing's less than or equal to m. For some m. And then we're going to show, now this is a non-empty set bounded from above, therefore it has a supremum. So then we do let C equal the supremum of F from A to B. Because at that point we're guaranteed it has a supremum. Since that was our last axiom. Remember our last axiom that we had. Every non-empty set, every bounded non-empty set of real numbers has at least upper bound, a supremum. Does that make sense?
Yeah.
So first we're going to show that this thing's bounded. Therefore this thing has a supremum. Then we need to show
That the supremum is included.
then there exists x naught in AB, use lowercase, in AB, such that f of x naught is equal to c. And then we're done.
C and C is the supremum.
C is a supremum. So show it's bounded. Since it's bounded, it has a supremum. Now show that there's some x in that interval such that the image of that x is a supremum. Or in other words, C is a member of the set. Another way I could have said that is show that C is in this.
Right.
Show that that set contains a supremum. That's everything that we need to do. Does that make sense?
Yeah.
So first I'm going to do this part, which I did last time, but we'll redo it. And then I'll continue this stuff.
So that's less than.
Show that it's bounded.
Right.
Right. Okay. So the way we're going to show it's bounded is proved by contradiction.
Assume that there's a member in there that is greater than.
So maybe we'll do the lemma over here, and then we'll go back to that. So prove if f is a function from a b to r, where f is continuous, then f is bounded. And we know what I mean by bounded, right?
Yeah.
And we'll just do bounded from above. Because we'll just do the uppercase. But obviously, from below is the exact same thing. Okay. So let's start with this side proof. Prove that this thing is bounded. This will do proof by contradiction. 1. Assume by way of contradiction that f is not bounded. What does it mean for it to not be bounded? It means for any natural number I pick, I can always find a number
Bigger or.
that f maps to bigger,
Yeah.
right? 2. Then, for all n in n, there exists x sub n in AB such that f of xn is greater than
Back down.
n. Does that all make sense?
No, we need to go over that line again.
So if f isn't bounded, then that means for any natural number you pick, I can find an input to the function that gives me an output bigger than your natural number. So if you pick 1, I can find x sub 1, so that f of x sub 1 is bigger than 1.
Okay.
If you pick 2, I can find x sub 2 such that f of x sub 2 is bigger than 2, etc. All right. So let's see. 3. How are we going to get our contradiction? So our contradiction is going to be, maybe I'll make a note here so that it's obvious what our contradiction is going to be. Then f of xn is unbounded and so does not converge. Right?
Right.
It can't be unbounded and converge. It can't take off to infinity and converge to a number. That doesn't make sense. Okay? So now I'm also going to get that f of xn converges to something, and that's going to be my contradiction.
How do we do that again?
Well, I haven't done that part yet.
I know, I'm just trying to think. But we say if it's bounded and
Well, so now, maybe say this. Observe that xn is in AB,
yeah.
comma, so xn, well, I'll just change it.
So there's a subset of xn.
xn is bounded.
And we know every bounded subset.
So there exists a subset of it such that the limit of x and k equals a exists. So that's kind of a lot going on here, but it's simple steps. So xn is in this closed interval, right? This sequence is in this closed interval. You good with that?
Yeah, but I thought we just barely defined it to not be in that interval.
No, that's what we did. That's how we defined xn. Xn is the element in here that makes f of xn bigger than n,
Okay.
right?
Yeah.
Yeah.
Bigger than any n you choose.
Well, x sub 1 makes f of x sub 1 bigger than 1. X sub 2 makes f of x sub 2 bigger than 2,
Right.
etc.
Oh, right.
Right? It's a sequence. It's an infinite number of numbers. You guys with me so far? You ready to go over this one?
Yeah.
Okay, so we know that xn is in AB, right?
Yeah.
Where?
It says there exists xn in
So that's how we know xn is in AB. One of the proofs you guys did, I think even on your test, is if we have a sequence in a closed interval, then that sequence is bounded. Right?
Yeah.
And then every bounded sequence contains a
Subsequence.
convergent subsequence. Any sequence you give me that's bounded, I can find a subsequence of it that converges.
Okay.
Good? So that means that since this is bounded, then there's a subsequence of it such that it converges, or it has a limit. We'll call it A. Or we'll actually call it x naught, for the sake of keeping up with, or following the way the book does it. We don't have a contradiction yet.
We do. Does not converge. Converges.
We're talking about two different sets. This sequence is in the domain. This is in the codomain. So now we need to use, always keep track of, we need to use all the information we're given. Okay, we use the fact that this is a function from A, B to R. What haven't we used yet?
F is
That's
continuous.
continuous.
The fact that's continuous. So I obviously need to use the fact that's continuous somehow to get a contradiction.
Well, couldn't our line 4 just be observed that f is continuous and you know that it doesn't converge? Oh, continuous convergence. Okay, never mind.
So, since f is continuous, the limit of f of x and k is equal to f of x naught. Oh, I forgot this important thing. No, sorry. Because I need to show that x naught's in AB. And that's by the, what was that called? The sequential compactness theorem, something like that?
If what?
So, remember big picture, well, I didn't spell it out here, sorry. I need x naught to be in, I need to make sure x naught's in AB. Okay? And the reason that I need x naught to be in AB is so I can use it for our definition of continuous. Definition of continuous is for any sequence that in the domain that converges to a point in the domain, then the image of the sequence converges to the image of the point. Right? So I need to show that x naught's in the domain. How do I show that x naught's in the domain? And that's, I think it's called the sequential compactness theorem. I can't remember exactly what
Why
it
don't
is.
you just show that the limit of it?
I don't do more proving, I just use the theorem directly. The theorem says if you have a sequence that converges in a closed interval, then the point it converges to is also in the closed interval.
Right, I remember that.
So that's more like a side note. Note by, I can't remember exactly what it's called, sequential compactness theorem or something like that. That x naught is in AB. And now I can use my definition of continuous with x naught. Because x naught's in AB, and this is a sequence in AB that converges to x naught.
Oh, therefore there is a sequence. Since it's continuous,
Yeah, so since
f of x is continuous,
F
there's a sequence f
is
of x that
continuous.
converges to f of x naught.
then the limit of, location. Then the limit of f of x and k is equal to f of x naught. Right? Since x and k converges to x naught, then f of x and k converges to f of x naught. Now remember where I told you that we were going to get our contradiction. So read this line again.
Oh.
Right, so one more thing I could add on to this, maybe I'll just put it here, which implies that the limit of f of xn is equal to f of x naught. And there's our contradiction. You see it?
How come if we prove that the limit of the subsequence converges implies that the limit of the sequence also converges?
I don't get how you can use the same image.
Probably should have one more. How's a better way that we can say this?
Oh, we're using that right there. I can actually totally see now.
Well, this falls from, I'm trying to think if this was an if and only if. Let me just think out loud for a second. So I'm thinking that every bounded sequence has a convergent subsequence, and if the sequence has a convergent subsequence, then it's bounded. So I should have said that. This implies f of xn is bounded. I think that's right. it doesn't converge to x naught necessarily. Right? Because it could have just been like an alternating sequence, for example. It might not converge at all. It's just bounded. That's right.
Well, I thought they have to converge to the same point if it's continuous.
That is true if this converges. If this converges, then every subsequence converges to the same thing.
Oh, I thought I thought we know it converges. 'Cause it's
We don't know that this thing converges.
But subsequence does.
But it's guaranteed to have a convergent subsequence. Well, in fact, we didn't even use that. We found out that it has a subsequence that converges. And that's how we know it's bounded. A sequence is bounded if and only if it contains a convergent subsequence.
Oh, I totally see them. And if it's bounded, then that is false right there. Line 2 is false if it's bounded.
Line 2.
Oh, well, line 1. There's our contradiction. Assume by way of contradiction that f is not bounded, and then at the bottom, f is continuous, then.
I still don't even think why I said it's true. If the sequence contains a convergent subsequence, then it's bounded. That's not true. But, I mean, we could just think about how this thing's defined and still see that it's bounded. Since this converges to something, here's a way to see it. That's still not a good way to see it. I feel like I have to put mucky argument to make this explicit. If this converges to something, then when I plug in really big values of n, they get closer to a single number. Like I want to sandwich this in a limit somehow. Like I want to force this to be monotone increasing or something like that.
Well, okay. Because you have a subsequence that is converging, doesn't your sequence converge?
No. For example, -1 to the n. Let's see, since f is continuous, then that implies, this doesn't imply that f of xn is bounded. But let's make sure we understand that. So, here's a better way to say it. Let's not make our contradiction there. Let's keep that. Let's keep that, and let's come here. Then f of xn is unbounded, and so is every one of its subsequences. That's an easier way to make it.
That's not true.
It is true.
Subsequence of f of xn would be 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2.
No, it can't. Because f of xnk has to be greater than xnk, which can get arbitrarily big. Try and put that aside note here so I can't insert it. Because f of xnk is always greater than xnk is always, oh sorry, not xnk, is always greater than nk. Is always greater than n. There's the side note. So this always gets arbitrarily big.
Okay.
Okay, so then, here's a contradiction. That's an easier way to think about it. Okay, I like that. So let's go over the logic one more time, make sure it all makes sense. Okay, so remember what we're trying to prove. We're trying to prove that this function has an upper bound. Right? So assume by way of contradiction that it doesn't have an upper bound. Then for any natural number you pick, I can always find an element in the domain that maps to a number bigger than the natural number you pick. That's what it means for it to not be found from above, right? I can always find a number bigger. So, this sequence is unbounded, and so is every one of its subsequences. And let's make sure that that makes sense. Here's the thinking for why it makes sense. I shouldn't even say it's bounded. I should have just said every one of its subsequences are unbounded. Because x sub n sub k, f of any one of its subsequences, by definition of how we made our function, this is always bigger than nk, right? And nk is always bigger than n when you create a subsequence. Greater than or equal to, sorry. You can pick the sequence itself. We've used this little piece of logic a couple times already. When you create a subsequence, the index in the subsequence is always greater than or equal to the index in the sequence.
Right.
So you good with this?
Mm-hmm.
So for any subsequence you pick, x and k,
That's gonna be great.
we can make it as big as we want. It's unbounded.
Right.
You good with that? Okay.
So subsequences
Then-
have to go to infinity too.
No, they happen to in this case, which is what I was trying to fidget
Well, what
with.
I'm saying is the n inputs have to go to infinity. The sequence can't have 4 indices.
Oh yes, there has to be an infinite number of indices. Yes, always and forever. A subsequence still is a sequence. It's infinite. Right? So we still have to use all those big massive numbers, all the big n's. Nk is always greater than or equal to n.
That's why it makes sense that every one of its subsequences.
Okay. So you good with every one of this function's subsequences are unbounded.
Yeah.
Okay, moving on. Observe that xn is in a b by definition. So xn is bounded since it's in a b. So it has a convergent subsequence. Now this x and k and this x and k are not the same thing. Up here we were saying for any x and k this is always true. Here we have a particular x and k. Make sense what I'm saying there?
There exists one.
Okay. Yeah, so there exists one subsequence such that the limit of that subsequence exists. So if a sequence is bounded, it has a convergent subsequence. Okay. And then by the sequential compactness theorem, or whatever it was called, if we have a convergent sequence in a closed interval, then what it converges to is also in that interval. So x and k is in AB, therefore what it converges to, x naught, is in AB. Does that make sense?
Yeah.
Okay, now f is continuous. So the limit of the image of the sequence equals the image of the limit of the sequence, which was just x naught. X naught is defined to be the limit of it, I think, right? So, this thing, the limit of this thing, is that, which contradicts it being unbounded. Good?
Yeah.
Sorry, that was kind of messy. Should have got my logic worked out at the time. Okay, so now let's do the second part of this, which is this over here. We're going to prove that. Now we're going to show that this thing, the image of this function on that interval, contains a maximum. So if f is a function from AB to R that's continuous, then f has a max element. Right? So, 1. Let C equal the supremum of f from A to B. And notice that that has to exist because this is a bounded set. Every non-empty set of real numbers bounded from above has a least upper bound, or a supremum. Call it C.
Wouldn't it be B? Oh wait, no. Keep going.
Okay. And let me think for a second how I want to do this. Well, if C's the upper bound of 2, then c minus 1 over n is not an upper bound.
Why are you bringing 1 over n?
Upper bound. So there exists xn in AB such that c minus 1 over n is less than f of xn is less than or equal to c. Okay, a little bit going on in that line, so let's make sense of it. C is the least upper bound of the function, right? So c minus 1 over n is not an upper bound of the function.
Right.
So in other words, there's some value in the domain so that when I plug it into the function, I get something bigger than c minus 1 over n. And c is still the supremum, so it has to be between those two things.
Okay.
3. So then, the limit of c minus 1 over n is less than or equal to the limit of f of xn is less than or equal to the limit of c, is just c obviously. Good? And that just gives us that c is less than or equal to the limit of f of xn is less than or equal to c, which gives us that the limit of f of xn is equal to c. Okay, so we found a sequence in AB whose image converges to C. Right? What we don't know is, remember where we're trying to get. We're trying to find x naught in AB such that f of x naught is equal to c. Okay?
Okay.
That's where we're trying to get. We found a sequence xn whose limit of f of xn is equal to c. But we haven't found x naught yet. And we know what x naught is going to be. It's going to be the limit of xn.
Yeah.
So let's see, 4. Since xn is in AB, there exists a so I don't know that xn has a limit, but I know since xn is in AB, the exact same argument we made over there, I know that it has a convergent subsequence. So since that is in AB, there exists xnk such that the limit of xnk is equal to x naught. We good with that? It's the same thinking we did over there. Every sequence in a closed bounded interval contains a convergent subsequence. That convergent subsequence converges to that which is in, sorry, I kind of did a lot in one line, x naught, which is also in AB. Kind of doing what we did a few steps over there in one line. So since xn's in a closed interval, it has a subsequence that converges to a point that's also in that closed interval. You with me there? All right, now we know that f is continuous.
And don't we have, if it's continuous, then it has a method.
F of x and k is equal to
I thought we already
f
knew
of x naught.
f was continuous.
Yeah, using the fact that f is continuous right here.
Oh, right there. There you
also equal to the limit of f of xn is equal to c, which gives us that f of x naught is equal to c. So, a little bit of thinking there. I have the limit of this sequence equals this, but this is a subsequence of this, right? F of xnk is a subsequence of f of xn. And we know that if a sequence converges, then all its subsequences converge to the same thing. So I know that f of xnk converges to f of x naught since it's continuous, and I know that f of xnk converges to the same thing as f of xn, which is c. Therefore, f of x naught equals c.
Where did, oh, right there.
You see all that?
Yeah.
Okay, so that is the extreme value theorem. And now I gotta send an email real quick before the afternoon starts. Sorry, I forgot to do this before class.
This is called the what value theorem?
The extreme value theorem. And we can do the same thing for a minimum. We just did the maximum in that case, right?
Mm-hmm.
I gotta order my presents.
Brother, I went to try to order 3 separate presents and they were out of stock. And they wouldn't be here till I changed my presents 3 separate times.
You're a lucky person. You're a lucky person, whoever you got presents for.
Oh yeah. I got Viv. She's literally gonna accept anything I give her. I got her a Packers blanket.
When did you get it?
A Roku, TV. Not like an actual TV. They call it Roku TV though. It's like an Apple TV. She just can't get Disney Plus on her TV. So she needs some
Pay for Disney Plus.
No, she's using Jared Dixon's subscription.
No.
Don't ask me how the connection did.
Okay, so that's the extreme value theorem. Next we need to do the intermediate value theorem. The intermediate value theorem is very similar. Gotta go back and do the nested interval theorem first. You remember that one that I skipped over that one time? You pointed it out, and I said something like, "We don't use this for a while" or something. But so the next section is going to be on the intermediate value theorem, which these two theorems are huge, by the way. They're probably the most
The
common
fact that if a
theorems that
bounded-
people mention in calculus.
The fact that a bounded sequence that is continuous is bounded. Or sorry, has an upper member. Or sorry, has a max member. Look down, look down.
That's not a good way to say it. Let me just talk it out first, since we'll have to do a separate proof here anyways. So we did one thing already. We said if I have a continuous function f on some closed interval, ab, so there's some closed interval ab, and I've got a continuous function on this interval, looks like whatever it looks like, from a to b. Then we said on this interval it attains a minimum and a maximum. Right? The second thing that we're going to say is, for any value you pick between f of a and f of b, notice this is f of a, maybe write it this way. This over here is f of a, right? And then this over here is f of b. You with me on my picture so far? So, if I have a function from a closed interval to the real numbers, from a to b, where we have f of a, f of b, then for any number c between a and b, I'm guaranteed that there exists x naught such that f of x naught equals c.
Okay.
That's what we're saying.
What?
F of x naught.
That's just like saying,
Pick a number c between f of a and f of b.
okay.
I'm guaranteed then, in the interval AB, there is some x naught such that f of x naught equals c.
That seems so intuitive.
The reason that seems so dang intuitive is because you were told that, think about continuous function as you can't lift it up when you're drawing. So when I go from this point to this point, I have to draw everywhere in the middle. But now think about our definition of continuous.
Our definition is for every limit of every x value, there has to be a corresponding y value.
Our definition is if a sequence converges to a point, then the image of the sequence converges to the image of the point.
Which makes sense right there.
Now, to go from that
That's
idea of continuous to, oh yeah, that's obvious,
Just a point or the same point?
write it out this way, it's easier to see it. Is it a domain and x naught is in the domain? Sorry, that's an equivocal usage of that. That's what it means for it to be continuous. If for any convergent sequence you have in the domain, then the limit of the image of the convergent sequence is the limit of what it converges to.
Is the image of the
Oh yeah, is the image of what that limit is. Another way we could, maybe a better way to say it, to see what exactly is happening is,
That is a weird definition of convergence.
if the limit of that,
You're just not used to it.
well, no, what I had there is fine. So yeah. So that's what we mean by continuous. And now to go from, oh yeah, as long as f is a continuous function, then this is always true. No, that is not obvious at all. Because you might be thinking your x sub n's could have all sorts of holes in there. Why would it have to, for sure, hit every single value between here and here?
It's got to be pretty rough.
You're saying because it's continuous in the sense that I can't pick up my marker to draw. How is that obviously true from the fact that if the limit of xn is equal to x naught, where xn and x naught in D, well, if f is a function from D to R such that for all xn where
For all xn.
yeah, then the limit,
So that word for all is like saying, don't lift up your pencil.
so here's what we're saying. We have f as a function from D to R, such that for any sequence in the domain you pick that converges to a point in the domain, then the image of this, the limit of the image of the sequence equals the image of the point. The idea that this captures the same information as if I draw a point or draw a curve from here to here, I have to touch every point in between, is not at all obvious. How do you go from that definition to that idea of continuous?
Why do I feel like
In other words, if I didn't say anything about continuous, and I just told you, look, we've got this function such that for any sequence you pick in its domain that converges to a point in its domain, then the limit of the image of the sequence equals the limit of the image of the point, you would in no way in your head say, oh yeah, we're talking about a continuous function.
yeah, but I feel like your C and your X naught are. I feel like we're proving a definition.
This is not an x naught. We need to find an x naught.
I know.
So we're saying just pick take your two endpoints in your closed interval. Your start of your D and your end of your D. Those give you two values out. We're saying now you can find for any number in between those two, you can always find a point in your domain that maps to that number. That's crazy. The thing that you get out, there's no holes in your image, in other words.
Okay.
Which is weird because your x ends, that skips all sorts of numbers.
I don't see.
Remember, x n converging to x naught, we're taking this. We're not hitting every point along the way.
Yeah.
Right? And yet we're always, for any number we pick here, I can always find something that would give me that number. That's what we're proving. It's not at all obvious.
That just doesn't seem.
Doesn't seem what?
That seems. I don't know. It seems
You-
very logical and.
It's a very logical end when I draw out this picture. It is not a logical end when you read this definition. Here's your definition. Now prove this.
We draw the picture again. Draw it like this. Draw 1 point of x and then 1 point of y. Of the domain and then how it correlates to.
Well, here's the domain, a, b, and then we have some function on that domain, which is whatever it looks like, some continuous function. Here's f of a.
There's your image of them. I just.
Here's f of b. Now we're saying for any value you pick between these two, c, then there exists x naught such that f of x naught equals c.
I'm talking. Okay, fine.
It just
Use
seems
the
very
definition of continuous on this.
That's
No, I'm saying. The definition of continuous is the limit of xn. It's not even going to look like the graph we just plotted. Because
right.
that's the
I
limit.
drew this f in here to make it clear to you what exactly is happening. But here's what we know. F is a continuous function. Therefore, if you have this point on the function and you have this point on the function, then we're guaranteed that I can find somewhere in between where I can plot this point C. And there will be an excellent, like, oh, step C somewhere in here.
Right. That's what we're proving.
That's what we're proving. That make sense? So before we prove this, we need to do what's called the nested interval theorem. The nested interval theorem, I'm not going to be able to remember what exactly it gives me. One of you guys want to turn to it real quick? And then just read it to me or something?
Yeah. Chapter 3.4.
2.3, I think is where it was at the end. It's at the end of the section. Here it is, 2.29. Nested interval theorem. Proof
Why did they put it in this lesson?
plus 1 is always a subset of In. And if the limit of AN minus BN is equal to 0, then there exists one and only one X such that X is in In for all N in N. And N comma and the limit of AN is equal to the limit of X. Okay, so there might be a lot going on in this definition, but it's actually a really simple idea. So take some interval, In, here it is. We'll draw out the picture, then we'll do the proof. So here's AN, and here's BN. So we're saying, if you've got this interval, and then from here on out, you always make your interval smaller and smaller and smaller, so that your next interval, whatever it is, AN plus 1 to BN plus 1, is smaller. Let's see how we're... Do you see the intervals I'm talking about?
Yeah.
This interval right here is In. This interval right here is In plus 1. And if you keep doing this process, so if your intervals keep getting smaller and smaller, well, let's keep trying. If your AN is always less than BN, meaning your AN plus 1 is always less than BN plus 1, your AN plus 2 is always less than BN plus 2, if your AN plus 3 is always less than BN plus 3. And if your interval length keeps getting smaller and smaller and smaller, and it's always a subset of itself, then there's one and only one element that's always inside every one of these intervals, and that's X. And it's going to be the limit of AN and BN. Does that make sense?
How do you know they won't cross each other though?
AN is always less than BN. So AN plus 1 is less than BN plus 1. AN plus 2 is less than BN plus 2. So the interval length is always going to 0. The left hand of the interval is always our next AN term. The right hand of our interval is always our next BN term. Then there's always going to be one and only one point in the interval, X, and that point is the limit of AN and it's the limit of BN. So once it makes sense, it should be kind of obvious. So if it's not obvious what I'm saying, I need to explain it better.
No, that makes sense.
No? Okay. So we're saying, if I've got a bunch of intervals, here's one interval, and I keep making my interval smaller and smaller and
How
smaller.
does IN plus 1 make it smaller?
Huh?
How does IN plus 1 make it smaller?
Everyone from
Because it's the interval from AN plus 1 to BN plus 1. So in other words, if my ANs are always getting bigger,
Then your bands are always getting smaller.
and my BNs are always getting smaller, that's not necessarily true. I can have my ANs stay the same and my BNs get smaller. Or my ANs always get bigger and my BNs stay the same. Or my ANs get bigger and my BNs get smaller. Doesn't matter as long as my interval length goes to 0.
and as long as
So if my interval length goes to 0, is what this part's saying.
If IN plus 1 is a subset of IN.
Yeah, so if we're always making our interval smaller,
Okay. And if the limit goes to 0. Okay.
and its length is going to 0, then there's always going to be one and only one point. Not always going to be one and only one, but we're only ever guaranteed to have one point always in those. So in other words, if I did IN plus 2 and I followed this rule, I would still have the X, whatever these two things converge to. Because all my ANs converge to X, so that's all the left-hand sides of my intervals, and all my BNs converge to X.
Feels like
That's
X
all the
is
right-hand
0.
sides. Huh?
It feels like X is 0.
It's not 0, it's just some number.
If your AN was 1 million and your B was 1 billion.
Let's try this again. So I let's start out with some interval. Let's use real numbers for a second. Give me a left-hand number.
3.
3. Give me a right-hand number.
7.
7. Okay. Now let's make a smaller interval. So that was the interval 3, 7. Now if we make a smaller interval and we keep following some pattern, not necessarily following some pattern, but if I keep making smaller and smaller intervals of this, so what's a smaller interval?
3 and 5.
3 to
4, 6. Let's keep it easy. So now we got 4. That was bad. 6. There's 5. And if I do it again, and if I keep following, making the left-hand values move to the right and the right-hand values move to the left, then I'm eventually going to keep going to the point where I've only got one element in there. Whatever they converge to, 5. So I'm saying 5, if the left-hand values converge to 5 and the right-hand values converge to 5, 5 is going to be in all these intervals.
Okay.
Well, that's not really what I'm saying. It captures the idea, but what I'm saying is, if we always make our intervals a subset of the previous interval, and if the length of the intervals goes to 0, and if the left-hand value is always less than the right-hand value, then there's one and only one element, 5, that's going to be in all those intervals. And it's also going to be what the left-hand things converge to and the right-hand things converge to.
Okay.
You with me now? Okay.
It doesn't have to be a midpoint, right?
No.
So what if I wanted it to converge to 3?
So you could have had, I could have had one like this, for example. I'll just give you one. I could have had 3 over here and 3 plus 1 over n over here. Okay, there's a closed interval. What's the number that's always in there? 3. Because the left-hand value is always 3, 3, 3, 3, 3, 3, 3, and the right-hand value keeps getting closer and closer to 3.
Okay.
So that satisfies it. Okay. Good with all that? Okay. 1. A and B and these sequences such that AN is less than BN and such that AN is less than BN for all N in N and such that the limit of AN minus BN is equal to 0. You good with all that?
Yeah.
Then AN is monotonically increasing.
Man.
Good? Now, AN is monotonically increasing and it's bounded from above. Right? AN is always less than B0, for example, or B1 if you start at 1. Are you good that this is monotonically increasing? Okay. Are you good that it's bounded from above? Okay. Since it's
And
monotonically
it has
increasing
a
and bounded
limit.
from above, it has a limit. So, since, I don't want to say since all that again. I'll just say then. You know what I'm saying. Then the limit of AN exists. And the limit of BN exists. Right? Of AN 4. Then an is less than or equal to a. Well, I don't know, let's do that. Well, sure. Then an is less than or equal to a, and bn is less than or equal, or b is less than or equal to bn. Is less than or equal to bn for all n and n. Since the limit of an minus bn equal to 0, then a minus b is equal to 0, which gives us that a is equal to b. So they converge to the same thing.
We're proving
This converges to 0 by definition.
We're using this to prove the extreme value theorem.
We're going to. Not the extreme value theorem, the intermediate value theorem. Then a is equal to b, and we'll also call it x. 6. Then an is less than or equal to x is less than or equal to bn for all n in n, which gives us that x is in every interval for all n in n. Okay. And we're done.
Three.
Follow all that? Anything weird? Anything we need to go over again?
That was a pretty easy proof.
Yeah, it's a pretty straightforward one. But it also feels like such a weird, arbitrary proof,
Yeah.
which is why I didn't go over when we first did it and decided we'd wait till we actually needed it to prove it.
Why is a equals b equals x?
So a minus b equals 0, which means a equals b,
Oh.
and I'm going to call that x.
I see.
That was such a cool way to say.
Okay, good with that?
Yeah.
Alright, so intermediate value theorem now. Actually, let's pause for just a second. Will you run to the office and get my prints?
There's another test for your class today.
Yeah, they got to do their midterm.
Oh my goodness, I thought they took one last week.
They did. They took their chapter test last week.
They have a test in every chapter.
They have a test on every chapter.
That's what we should be doing.
While he's grabbing those, can I please go to the bathroom?
Yeah, go ahead.
Prove that for all natural numbers, and then,
Could we do some of your proofs?
why did they even bother with this?
Do they do proof by induction?
Yeah, they do proof by induction. And I tell them all how terrible my calculus students are at it.
Their extra credit, is that proof by?
Yeah, proof by induction. Binomial theorem. We should prove that in this class. You guys should know how to do that.
Binomial theorem.
Yeah.
Can you make 31?
Only had one student who's done that so far.
Levi?
No.
Taylor.
Yep.
Oh,
That was so good.
it's on the very back.
So is this midterm already more than your whole class doing in a whole year? you're so far ahead of last year?
We haven't had any holdups like we did last year. So I have 2 more chapter tests to go over with that class, and then that's everything we did last year. So far we've done 5 chapters, and we only have 2 to go.
How many chapters are in the book?
A lot. You don't do the whole book. The book is designed based off of your discrete math. You touch on a lot of fields. Not like this class where we're just working on analysis of the real numbers. You touch on a lot of different stuff. And depending on what the focus of your class is, you would use different stuff. So the author breaks it up for you depending on how you want to do it. If your focus is more on abstract algebra, there's a way to go through it. If your focus is just more on proofs in general, there's a way to go through it. If your focus is more on programming, there's a way to go through it because it's a common programming course.
So are you perfectly on par with your syllabus?
No, because we had that one weird day where I had to let him out early.
Oh yeah.
But I always leave like 3 days that I don't plan anything in my syllabus because he kept me. You never know what's going to happen.
I thought you were here with that this classroom.
Huh? What did you say?
I thought you were here with that. One of the people who just come to this classroom and they go, ooh, sorry, wrong class.
I don't know how anybody can get the wrong class in a school this small.
Do you remember? We've had like 8 in this class. Oh, I guess you're not in Jonathan's class. They gave it for Jonathan's. Crazy, huh? He's crazy. Ray's crazy.
Stupid people.
Okay, so let's prove this here. Let's make sure that we understand it, although I think you guys pretty much do. So if I have f from some closed interval to r as a continuous function, then for any point c between fa and fb, there exists some x naught in the open interval ab such that f of x naught equals c.
For all. So this is using the same proof that we just used. Or that we just did.
This is using it.
Is it using it?
Well, so far that's just,
Well, why I say that?
We haven't
I
used
look at-
anything yet.
I look at C.
it's definitely going to use a nested interval here, for sure. Okay, so here's how we're going to make our intervals. Maybe let's draw out a picture of how we're going to do this proof and then do the proof. And that will probably help. So, draw a picture off to the side here. We've got some function. We need to draw intervals, so I need to give myself some space. So here's B. We're going to assume as we do this proof that f of A is less than f of B, but it doesn't matter. You'd have to prove both cases, but we'll make it one. So we'll say the function, maybe the function looks something like this. Maybe, well, f of A, f of B, is right there. And then we got some point C. We'll pretend that C is coordinate here. So there's C, and we're going to be looking for the x naught, which is that point. So we're going to start out with the interval AB. So our first interval is going to be AB, which is this. Here's I1, our first interval is going to be that big. And then here's how we're going to find our next interval. We're always going to cut it in half. But we're going to cut it in half choosing the side that C's on. So maybe I need to draw both side by side and draw the picture as we go for you to see it all in action. One, let I1 equal the closed interval AB. 2, let maybe say it this way. Let A1 equal A, B1 equal B. 2. I need to find the midpoint of those two things. Comma. And let M1 equal their midpoint. B1 plus A1 over 2. This is how we're going to do our midpoints in general. So maybe like that. If now, do they use function notation? No, they just kind of break up into two cases. So we'll do that. If f of mn is greater than or equal to c, then an is going to equal, let's see, if our midpoint, let's do less than c first. If our midpoint is less than c, then we want to move a over to our midpoint. A(n plus 1, our next a, and our next b is equal to our previous b.
What are you doing?
Sorry.
I'm lost.
I know you are. I need to draw both the math and this thing as we're going, so that you can see what this is recursively defining.
Oh, I just bumped my foot. Right in the middle of my foot.
Okay. So we're going to make nested intervals. And here's how I'm going to do my nested interval. So I'm going to make my first interval start out with just AB. Okay?
Okay.
And then I'm going to take the midpoint of AB, which is right there. And I'm going to look at the value at that point. If the value at that point is less than C, I'm going to choose this interval. I'm going to choose the right-hand interval.
Okay.
If that value happens to be greater than C, I'm going to choose the left-hand interval. That way I'm choosing the interval that still contains C.
Yeah.
Yeah.
So let's see it in action just a couple times. So here's A1, here's B1. Then I may come and here's my midpoint one, right? My first midpoint. Well, C is greater than the function value there, right? So now I'm going to make this one A2, and B2 is the same as B1. And now my midpoint's right here. Here's M2. Well, at M2, we're greater than it, right?
Yeah.
So then, my A3 stays, and my B3 is over here.
Isn't this like,
And I pick the midpoint, and I do it again.
this is the same concept, different?
We're going to use the nested interval theorem. I'm intentionally picking intervals whose length go to 0, where my A's are always less than my B's.
Right.
Which is what the nested interval theorem needed. So that's what I'm saying. I'm saying set A1 equal to A, B1 equal to B, and always define the midpoint like this.
Mm-hmm.
Then if the function at my midpoint is less than C, that's right here.
Is C the point you were just randomly given?
Here's C, yeah, C is my random point. If the value at my midpoint is less than C, which it is in this case, then I'm saying make my next A the midpoint and keep my next B the same.
Makes perfect sense.
Yeah.
Then if it's greater than...
If it's greater than, keep my A the same and move my B to the midpoint. So I'm always cutting my interval in half, and I'm picking which half to keep. Does that make sense?
Yeah.
And I'm just picking the half that contains the C. So, ignoring the whole big picture for a second, let's say my C was right here. Here's my A, here's my B. There's A1, B1. When I take the midpoint, I'm obviously going to pick this interval. And then when I take that midpoint, I'm obviously going to pick this interval. And when I take that midpoint, I'm obviously going to pick this interval. And when I take that midpoint, I don't know. we'll probably pick this one, but you see how we keep going on, making our intervals smaller and smaller and smaller and smaller, right?
So why do you want to do that?
I need to use my nested interval there. I need to get this x naught such that f of x naught equals c. And the way that I'm going to get that is that the limit of an equals that x naught, the limit of bn equals that x naught.
Okay.
Well, let's just write it all out now. Maybe keep the picture there. Yeah, so write out the conditions for the nested interval here. Then, for all n in n, a sub n is less than or equal to, they better have, a n plus 1 is less than bn plus 1 is less than or equal to bn. Right?
Yeah.
My ANs can only move to the right, so they can only get bigger or stay the same. And my BNs can only move to the left
So why is it
or
plus 1?
or stay the same. Huh?
Why is it plus 1 then?
My next B term is less than or equal to my previous B term. My next A term is greater than or equal to my previous A term. And my A's are always bigger than my B's.
Okay.
Yeah, that has to be the case.
Your A's are always bigger than your B's?
Or less than, sorry. Yeah. So then that, comma, and f of am plus 1 is less than or equal to c, and f of bm plus 1 is always greater than c. Three, since bn plus 1 minus an plus 1 all over, well, how do I want to say that? Yeah, that's not bad to say it. Since bn plus 1 minus an plus 1, that's not the way I want to say that. Sorry. Since bn plus 1 minus an plus 1 is equal to bn minus an over 2. So let's make sense of that. This is saying we always, our next interval, notice that this gives me the distance between these 2 points. The distance between these 2 points on our next interval is always equal to half the distance on our previous interval.
On our previous.
Yeah, this is the previous, this is the next.
Yeah.
Right.
So this distance is equal to half of the previous distance. So since that, then
We're trying to prove
bn
that
minus
converges.
an, we need to say that the difference in their limit is 0. So remember,
Right.
yeah, for that previous theorem that we just did. So then bn minus an is equal to b minus a over 2 to the n minus 1.
Yeah.
2 to the n minus 1.
Yeah.
Last term. We're going back to the last term.
So the nth term, what's the distance between these 2 terms, the nth terms? It's b minus a, our original distance, divided by 2 to the n minus 1. So, for example, let's look at one example. Let's see, what's b3 minus a3? What's that distance in terms of b and a? How many times did we divide b and a in half to get 3 times?
What? Twice.
Twice. We did b minus a, and we divided that by 2 twice.
Oh, okay.
Yeah.
So the distance for the nth terms, that means we divide by 2 n minus 1 times
Okay.
of our initial distance. And what we were trying to get with that is then the limit of this, of bn minus minus an is what?
Oh.
Which is what we were trying to get. So now we can use the nested
That was
interval
tricky.
theorem.
Then the limit.
Tip.
The limit of this equals the limit of this equals 0. Probably should have put that middle piece in there. You see it? Okay. So now we can use the nested interval theorem. So 5. Then there exists x naught such that the limit of an is equal to x naught. The limit of bn is equal to x naught. And an is always less than or equal to x is always less than or equal to bn. Yeah, you see that?
That is our definition of the extreme
That's what
value.
the nested interval theorem gives us. So the nested interval theorem basically says, look, if this is always the case,
Okay.
and this is the case,
Yeah.
then this is the case.
Won't 4 always be the case if 2 exists?
Won't 4 always be the case if 2 exists?
Yeah, if that inequality is happening.
No. Think about if A was a constant 1 and B was a constant 2.
Okay. Because they're equal to each other. They can be equal.
They can be equal, but they don't necessarily. The A's and the B's don't have to approach each other. Maybe A's approach 1 and B's approach 2, and there's a gap. So this is saying AN's monotonically increasing, BN's monotonically decreasing, and the distance between them goes to 0. Then they limits are the same thing, which is a point in the middle of them. That should be an x naught.
Right.
I see. A bit.
Okay.
So now x naught is in AB. Maybe this doesn't need to be stated, but let's try it out. Then the limit of both these things is x naught equals the limit of bn equals x naught is in AB. Let me go in the middle. Let me see. Okay, yeah, that's fine. So then the limit of the image, now since f is continuous, the limit of the image of this equals the limit of the image of this equals the image of this. You with me on that?
Yeah.
Then the limit of f of an is equal to f of x naught, and the limit of f of bn is equal to f of x naught.
How come they had a C? Also there.
Yeah, so then the point is that x naught is then going to be our C value. So just skip straight to CN. Oh, that's upset. Since f of an is always less than c, the limit of f of an is less than or equal to c, which gives us that f of x naught is less than or equal to to C. And then similarly the other way. 9. Since f of bn is always greater than C, the limit of f of bn is always greater than or equal to C, which gives us that f of x naught is greater than or equal to C, which gives us that f of x naught equals C, which is what we're trying to get.
I still feel like that doesn't fit. It feels like it still doesn't fit. It feels like x naught could be a little bit off.
Could be a little bit
Like-
like, what do you mean by that?
Or
Oh, actually,
we're
never-
trying to get our x naught
I see.
as close to C. We're
Well,
converging
x
to
naught,
C.
it converges, B and A both converge to C, or to x naught.
Yeah.
And for x naught to be a little bit past C, then that means that one of them is including C, right? You see what I'm saying?
Let's just go over it one more time. So you're good with how we're defining our intervals?
Yeah.
Yeah? Okay. So you're good with this is always true.
Yeah.
Now, I don't know why I did a +1 there. I just copied what the book said. Which gives us that's always true.
Yeah.
Okay.
If it's true for that, it's obviously true for +1, right? Saying the same thing. So this is always less than C, and this is always greater than C. Right? Okay. Now, we also know that the limit of this goes to 0. I think you're good with that, because the interval goes to 0. So, then the limit of this thing equals the limit of this thing, which is x naught, which has to satisfy this inequality.
Okay.
You good with that? So, okay, here's where we explicitly say everything we need. The limit of this equals the limit of this equals x naught is in that interval. Now it's a continuous function.
Yeah.
So the limit of the image of this equals the image of that, and the limit of the image of this equals the image of that.
And you said that down there.
So, the limit of that, which is what we're saying right here, right?
Yeah.
Now we already knew this information,
Right. Up there.
which gives us this. And we already knew this information, which gives us this.
Oh. If it is less than C and if it's also greater than C, then it's
Less than or equal and greater than or equal.
and equal.
Yeah.
And it's equal.
I see.
Anything weird?
No, I see.
Oh, geez, we're way past. Sorry.
It's fine.
Okay, that's it. We're good.
Do you want these tests back?
You didn't finish mine, you want?
Yeah, I need to grade them still.